I think we are live now.
Okay. Okay, I think we can get started. Welcome everyone to our Safari Live seminar. This time we have Professor Jian Huang from University of Illinois Urbana-Champaign, EC department. He's an assistant professor there. He's been there since 2017. I believe he got his PhD from Georgia Tech. And he works on the intersection between computer architecture, computer systems, with a lot of focus on memory and storage systems, system security, and distributed systems. And today he's going to talk about storage systems. And he's done a lot of work in this area, and he's received some awards, Best Paper Award at Usenix ATC, for example. I think without further ado, I'll let Jian take over. Jian, please go ahead. And if there are questions, I guess before you take over, sorry, if there are questions, please, if you're on Zoom, please feel free to ask. If you're on YouTube, you can submit your questions and we'll find a good time to deliver those questions to Jian.
Yeah, so please feel free to ask questions during my talk. So thanks for the great introduction, honor. And so this is my great honor to have a chance to introduce our recent research on storage system. So my talk title is the SA of storage system and interface specialization and approaches. So in today's talk, I'm going to discuss the three aspects of building storage system, interface specialization and approaches. I'm also going to use some of our research here to convince you to deliver the message that why these three aspects are important in building storage systems. So so when we talk about a storage system, it's actually not just happened recently. It has a long history. So in the Stone Age, the cavemen actually used the stone to draw the pictures on the stone to keep the information, right? So in the paper age, and we invented the papers, and also we invented the pens, and to write down the knowledges we wanted to keep. And in the digital ages, we have the hard disk drive, and of course, when we build the file systems to access the hard disk drive. And if we study this trend, and you may already realize actually different storage medium actually requires different interface. So for example, in the Stone Age, we have the stone, and the interface between the stone and the medium is actually very different from the way how we write down the words on the papers. And also in the digital age, and we invented the file system. And later on, we have the flash memory. And at the beginning, the flash memory is not that fast. So that's, we actually reuse the file system to access the flash memory medium. But what if the performance is much faster than the hard disk drive? And that's actually really happening, over the past decades, right? Compared with the hard disk drive, the flash can deliver, 5,000 times, higher throughput and reduce the access latency by 100 times. So we started to think about, what's the interface which should access the flash memory? And so this actually come to my first research question. So how should the interface look like for modern storage system, right? So for flash memory, and which is much faster than hard disk drive, should we still use the traditional block interface? And this is the first research questions I want to address in today's talk. So interface is just one factor that's going to affect the storage performance. And there are also many other ways we can do to improve the storage performance. For example, we can build many specialized storage devices. And one typical example is the computation storage, right? So we can offload the host functions into the storage devices so we can overcome the PCIe bandwidth bottleneck. And of course, we can also develop software-defined storage and to make sure our storage stack has a predictable performance. And then later on, we also have the persistent memory. For example, and Intel released the 3D Exponent a few years ago, right? So actually, we can keep the list going on. And we have already seen a rich set of specialized storage systems over the past decades. So this actually comes to the second research question. And should we keep the list going on should we thinking about what's the final purpose of building specialized storage system. So in today's talk, I'm going to use some examples to show you that the final purpose of building specialized system is to generalize them, right? So, and we are going to discuss that, okay? So when we build many different types of specialized storage system, and we realize actually today's storage system is very complicated. So it's not just a single, simple stack. We have the application, file system, storage hardware. It's actually a very complicated ecosystem. So when we extend this system architecture, and you can see, right? So we have, above the storage hardware, we have the low-level device drivers, and we have the PCIe modules. We have the IO scheduler, generic block interface, a virtual file system, and also build, based on the file system, we also build our own system infrastructure, for example, cloud storage infrastructure. And then we run many different applications like database and graph computation, and even machine learning workloads. So the stack is becoming so complicated, and this is going to cause many, many issues. So for example, today's storage software lacks practical performance, and because the entire cross-layer stack is so complicated, it's actually very hard to achieve practical performance. And this is also the reason why it's harder to guarantee the tail latency for today's applications. And also, the storage software is very slow. And we further improve the performance of storage hardware. For example, today's hardware devices, we can reach 10 microseconds, but the software stack will take 15 to 20 microseconds. So it's very clear that we have to address to elevate the storage software overhead there. And also, the storage software is energy intensive. So for example, in our previous study, and we measure the energy consumption of the storage software and realize actually the software is going to cost 110 times more energy than the hardware, than the flash memory device itself. And this is also true for data centers SSD. And also, we developed the storage software stack for decades, right? So about 60 years and 70 years. But we still realize there are many, many vulnerabilities there. And the storage software is still vulnerable to many malware attacks, for example, the ransomware, right? So we can, build to address each of these questions, and we can build a specialized storage system, right? For example, to improve to make sure the storage system deliver critical performance, and we can leverage the software-defined storage, right? And to reduce the storage software overhead, we can bypass the OS kernel, and we can even use the flash as memory. So there are many ways we can do, and we call this as a specialized system. But this actually comes to the third research question. So what's the right approach to developing a storage system today? So we have so many issues, and the storage system is becoming so complicated. And should we still use the heuristic-based approach or human-driven approach, or should we use a different approach to develop, the future storage system? And also, the application is keeping increase their demand on storage performance, and they wanted to get a good performance as soon as possible. And how we can make the system, adjust the stack and to satisfy applications requirements on performance, capacity, and many other things. So in today's talk, I'm going to try to address these three research questions, okay? So, and that's actually the reason why I started to think about, what's the core of building storage system? And I summarize as interface specialization and approaches. So when we talk about the interface, I mainly talking about the block interface versus the byte interface. So I'm going to use one example to demonstrate that why we should go for byte interface today and why it's feasible to go for byte interface today. And then when we build a many specialized, storage system, and we are going to ask ourselves, what's the final purpose of building specialized storage system? Should we keep going with the software-defined storage, or should we try to make them becoming more generic? And also for the approaches, and should we still use the human-driven approach, or should we use the learning-based approach? And I'm going to use some examples to show you that why learning-based approach is promising today. So I summarize, and this is three aspects as the ISA of the storage system: interface, specialization, and the approaches. So during my talk, please feel free to ask questions, okay? So now I'm going to talk about the first aspect, the interface, right? So this is the storage stack. I think everybody get familiar with you learn this knowledge from the operating system and architecture course, right? We have the application, and we have virtual memory and the file system, and we have the flash-based SSD. And as we discussed in the beginning, and when the SSD came out on the market, we actually used the block interface, and we built a file system and to support the SSD. And based on the block interface, we actually built the paging mechanism, right? So when the host access the data on the SSD, and every time we have to access the data under the page granularity. And this is actually going to introduce many fundamental issues. So let me discuss one by one. So if we rely on the paging mechanism, and this is going to store the process, right? So for example, we memory map SSD into the DRAM, and when we access the data, if the data is not in DRAM, and your host instructions will be stored by loading the data from the SSD. So this is going to store the process, and also because of we use the paging mechanism, and this is going to introduce a high I/O traffic, right? So sometimes even though we just modify a few bytes in one page, we still need to load the entire page from the SSD, and this is going to cause the high I/O traffic. And also depends on your application's locality, and then this is going to cause the DRAM surviving or pollution issue, right? So, and the host application may not fully utilize all the data in one page, and that's the reason why if you have bad locality, and the DRAM surviving issues will happen. And also, when we work on the storage system, we have to guarantee the crash consistency and the data durability. And when we guarantee this data durability, and by default, we have to enforce the page level persistency. And the page level persistency, the overhead is much higher than the byte level persistency. So what if we can enable the byte interface for SSD? And this is going to change the way how we build the file system, and it's going to change the way how we access the data, and with the through the SSDs. So we develop our work called Flash and try to explore the byte accessibility of SSDs. So with the byte interface enabled by the SSD, we actually can allow the CPU to directly access the data and in the SSD and through the cache 9 granularity. And in this case, we actually can avoid the paging. And so we can reduce the I/O traffic, and also we can reduce the DRAM surviving and the pollution issue. So for example, if your application has bad locality, and you actually can allow the CPU to direct access the data and in the SSD, you don't need to cache the data in the DRAM. And this is a very simple way for us to reduce the DRAM surviving and the pollution. And also, we can enable the fine-grained data persistency. And this is a very useful property for enabling the high-performance crash consistency, right? For example, in file system, we have so many metadata, and we don't need to rely on the page mechanism to persist this metadata. We actually can just persist the tiny bits bytes of the metadata in the file system. And enable the data accessibility of SSD. This is fully feasible today. And this is not because we can access the flash chip through the cache 9 granularity. It's mainly because we have the DRAM inside of the SSD container. And also the PCIe support the cache 9 granularity access today. We actually can use the memory mapped I/O interface and of the PCIe, and to allow the host to directly access the SSDs and the cache 9 granularity. And also to enable the data consistency between the host machine and the SSD, we actually can leverage the existing cacheable access protocols. For example, the OpenCAPI, but today we talk, it becomes CXL. So with these existing technicals, the DRAM buffer enabled in the SSD kernel and the PCIe MMIO interface, and also the cacheable access protocols like the CXL, we actually can support the better addressability for today's SSDs. Okay, so now we support the better interface for SSDs. And in traditional architecture, when we access the DRAM, we can access the embedded interface. We also have the paging mechanism, and we can access SSD through the block interface. And allow today, with the better addressable SSD, we can allow the host CPU to access the data and through the better granularity and for the SSDs. And this is actually going to increase the complexity for us to manage the system, right? So we have to, it's harder for to let the applications to decide which interface they should use. And so this is introduce the complicated interfaces and for applications to manage it. So the way we have to the way we simplify this management is that we propose a unified memory interface. And that's actually the way why we propose that the bad interface for all the memory and the storage devices today. And to support the unified memory interface, and we can use two approaches. One approach is that we can use the software-based approach, and we can use the traditional memory mapped interface. And this has already been done in today's OS, right? We can memory map the flash memory into the virtual memory, and then we unify the address translation. And so let me give you one example is that, so if the applications access the unified memory space and they have a virtual address, and then they are going to do the page walk, right? So we are going to walk through from the higher level to the lower level. And then the shared leaf level page table is going to tell you where is the page. And we can either point out of the page to the flash memory. So if the page is not in the DRAM, the page fault will happen. And then we are going to bring the page to the DRAM. And then we are going to update the unified address translation table. So next time when we access the page and we go through the page walk again, and we can direct access the data from the DRAM. And because the DRAM capacity is limited, of course, we are going to evict some flash pages from the DRAM. And when we evict this page out from the flash, and we just update the PTE entries and flash the TLB. And then next time we'll access the data, and you can rely on the unified address translation to access the page in the flash. So this is the software approach to support the unified memory space. Actually, there we can also rely on the hardware approach. For example, today's the memory semantic SSD proposed by Samsung. They actually try to put the flash memory into the unified physical address space. So the flash memory is just part of the unified physical address space. So now we finished the discussion on the bad interface and the block interface support with today's flash-based SSD. This actually opened a new direction and for us to work on the storage system. And now we are talking about how we get a good performance, right? So when the CPU directly access the SSD, we actually use a real FPGA board to test the latency, and it will take about 4.8 microseconds to access the one cache line in the SSD. But it's still much slower than we access the data in the DRAM. So how to solve this problem? The idea is that we can do the background page promotion, right? So and promote the SSD, the page from the SSD to the DRAM will take about 12 microseconds. And of course, we cannot put this promotion on the critical path. We try to remove this from the critical path by running in the background. So that's what they call the background page promotion. So we actually changed the root complex and to integrate our new promotion look asset buffer. So we have our algorithm designed in the SSD kernel and to decide which page we should promote. So we actually, when we decide the granularity and for the promotion, we actually use the page granularity. And when we promote, we actually promote the pages cache line by cache line. And then the promotion look asset buffer is going to track which cache line in the page has been promoted. So we use this way to avoid the conflict when the CPU access the data and during the promotion. So the PLB has 64 entries, and each entry has about 28 bytes, and to track whether this cache line in the page has been promoted successfully or not. And I'm not going to discuss the details how we finish the promotion. And if you're interested in this part, and please refer to the our ASPAS paper and for the details. Now we finished the discussion on how we ensure the consistency with the background promotion. Let's discuss how we enable the better granular data persistency. And this is actually quite similar to the way how we enforce the memory persistency for persistent memory. When we use the persistent memory or long-term memory, and we have to ensure the memory persistency as well. And this is similar, and when we enable the crash consistency or persistency for the bad addressable SSDs. So we have the CPU, and we have the processor cache, and we have the host bridge, and we have the SSD cache, DRAM cache inside the SSD controller, and this is a volatile. So because the processor is going to cache the data, so to enable or to enforce the data persistency, and we have to call the CL flash or CL double B to flash the data cached in the processor cache into the host bridge. And we are going to verify the address and disable the promotion. And this is because for the data that we wanted to make them becoming persistency, and we have to disable the promotion because the DRAM is still volatile, right? We don't want to promote that the data that should be becoming durable or persistent to the volatile DRAM. And after we finish this verification, and then we are going to use the write verify read to make sure the data really goes to the better addressable SSD. So this is the way how we enable the better granular data persistency. And we also, provide a very simple API for applications to specify the persistent memory regions in the flash memory, right? You just use the create PMEM region. You can specify the address space that you wanted to enable or enforce the data persistency. And then the flash by itself is going to disable the page promotion for persistent memory regions. So yeah, go ahead.
Yeah, Jian, sorry, I have some questions. So the first one is basically when we use a byte addressable SSD access, how can we saturate the SSD, external bandwidth? Do you think is that basically, because the one good thing regarding reading pages of data is that we can saturate a PCI Express bandwidth, no?
Yes, that's actually a very good question. When we use the byte addressable SSD, we still keep the block interface. Right? For example, we still have the background promotion. The promotion is still use the block interface. And you still can use the block interface to try to saturate it. And we use the byte interface is just because, for example, your application has the bad locality, and you just wanted to access one cache 9 in the SSD.
I see.
And use the byte interface.
Yeah. Okay. I have also some one more question, which is, regarding this, which I guess is, maybe we can have it later in the discussion. Yeah. Because if the application has very bad locality, why should we actually move the data outside the storage? Having some computation close to the storage or inside the storage can enable, I guess, more efficiency.
So that's actually the problem caused by the traditional paging mechanism, right? So so we just get used to the page mechanism, and so you have bad locality, you just load the entire page to the host DRAM, and we have the page cache there. And then now, if you realize you have bad locality, you just directly allow the CPU to access the cache 9, and then you are done. And then you don't need to cache the data in the DRAM.
Yeah, I agree. That's actually, one solution to this problem. But another solution would be considering near data processing, I guess, or in storage processing.
Yes, that's actually the specialization we are going to discuss later.
Oh, I see. Yeah. Okay, thank you.
Okay, good. Any more questions? Okay, great. So as I discussed in the beginning, right? So if with the byte interface provided by the SSD, and we actually can, open a new direction for system design, right? So in the traditional, system software, we actually, fully rely on the block interface to build the software stack. Now with the byte interface, and we're actually going to think about the system software design. So I'm going to give you some example. One typical example is the file system, right? So the file system, we have the metadata. We are going to build an index to index the data in the file system. And actually, we have many iLoads, and each iLoad represents a Y file. And then because we rely on the block interface, and we compact many iLoad together, and every time, even you just modify one file's metadata, and you have to flash the entire data block to the SSD and to the disk to ensure the crash consistency. And this is going to actually increase the I/O traffic, right? And also cause the long latency when we enable the crash consistency, right? So with the bad interface, we actually, every time when you just modify one inode, you just need to flash the persistent this inode. You don't need to flash the entire block. So this is one benefit we can bring to the file system. We actually try to build a new file system to support the bad addressable SSD. And another use case is the database applications. And this is the application, right? So in traditional way, and we are going to place the database tables in the persistent storage. And because they assume the interface is the block, and they actually have a centralized log buffer, and they try to compact many logs together and to saturate the storage bandwidth. And then the problem is that because we have a centralized log buffer, it's very hard to increase the concurrency of the database, and because of the log contention. And with the bad interface, we actually can distribute the logs. And then we actually can build a distributed decentralized log system and for the database. In this case, we can improve the concurrency of the transactional database. So this is another example which shows that the bad interface of the SSD can actually benefit either a system software or applications. So now to show that how we implemented the flat flash, and so we actually have enable the bad accessibility with the PCIe memory map interface, and we can use the OpenCAPI or CXL and the protocol to enable the cache, the data consistency between the host machine and the SSD, and we can also build a unified memory interface to simplify the management of the diverse interface like block and byte. And then we also enable the off-critical path page promotion, and because we still wanted to best utilize the high-performance DRAM. And also we support the better granular data persistency, and this is actually introduced the performance benefit for today's system software and applications. So we compare the flat flash with some existing approach. For example, the very standard approach is the memory map, right? So we can use the OS memory map interface, and we still use the paging mechanism. And we can also use, compare with the flash map. Flash map is actually an advanced version based on the memory map, and they try to have a unified address translation. And so because they have a unified address translation, they can save the memory consumption of the address translation tables. And this will bring some benefit to applications. And we use many different data-intensive workload, for example, GraphQL and Redis and key-value store, and also the traditional transactional database. And also, of course, the file system benchmarks. So let me show you the benefit of the flat flash, compared with the memory map and the flash map interface, flash map solution. And the flat flash actually can perform 1.6 times better than flash map. This is because we can reduce the paging overhead, right? So if you look at the lines, and the lines actually count the I/O traffic, the number of pages migrations when we run the applications. And because we support the bad interface in the SSD, the flat flash can dramatically reduce the number of page migrations during the application's execution. So this is actually the way how we get the performance benefit and from the bad addressable SSDs. And this is the benefit we demonstrated for the data persistency for file systems. We actually run many different types of file system benchmarks, and most of these benchmarks actually are metadata intensive. So for example, create a file, rename file, and create directory. And for this kind of benchmarks, they are going to modify the metadata of the file system. And also for the web server and the rail mail, actually they are also going to create many small files. And then they are also, these applications, they are also metadata intensive. And with this experiment, we show that the flat flash actually can reduce the metadata persistency overhead of file system by up to 18 times. Okay, so to summarize the flat flash work, actually, and we show that when we in traditional way, when we access the storage, we rely on the block interface, but we actually can also access the data with the byte interface. And this is one thread of research in my research group. And also, of course, to support the byte interface, we can also rely on the tradition. We can also rely on the recent long-term memory research, right? For example, my research group also did a lot of work on in the persistent memory space. But with the persistent memory and with the better addressable storage, and the vision and we wanted to develop is that we wanted to enable the better addressable everywhere. And this is actually the interface we wanted to achieve when we build a storage system. Is that and with today's CXL, and we can get all these things together, right? So we can get the better addressable storage and also the non-volatile memory connected through the PCIe, through the CXL protocols. So any questions about the interface part?
Professor, I have a question on the interface. So do we need an interface like malloc for the applications to use the byte addressability of the storage devices, or I mean it's all at the kernel space, like how you showed mmap as another comparison point. So is it something transparent from the applications, or do we need changes in the application as well to use such a?
This is actually going to transparent to the application. So because we have a unified memory space, and you can still use the malloc and to allocate memory regions from the unified memory space, and then so you can still use the existing library and to do so, to do the memory allocation. Actually, we are also trying to figure out how to design a new memory allocator and for CXL-based memory and storage systems.
Okay, thank you. I have another small question on. So in the last few years, there was also this talk about NVDIMM devices, which try to also provide some byte addressability by putting some DRAM and SSD in the backend. So, so how do you kind of look at those class of devices? And I think this enabling this in commodity SSDs is a very interesting direction. So, but I just want to know your opinion on those devices.
That's also actually a very good point. So I think when Intel turned down their 3ds point of optime persistent memory. Actually, we are thinking about what's the future of the long-term memory, and I think for the NVDIMM you mentioned, and with the DRAM battery-backed DRAM plus the flash, that's actually another way how we enable the persistent memory and in a short term. But I don't think this can really scale, right? Because for the NVDIMM, you actually still rely on the battery-backed DRAM to enable the data persistency, and actually. Even for today's commodity SSD, and we can also enable the better addressable, battery-backed DRAM inside of the SSD kernel. But for the NVDIMM, I think this is also part of the story, and because it still has some scalability issues. I don't think this is a long-term solution, but this is definitely a very good short-term solution.
Okay, thank you.
Okay, thank you. Any other questions about the interface? Right. So, to quickly summarize this part is that, when I work on the storage system and we just get used to the block interface, and the entire OS and the file system actually will, developed based on the block interface. And we are going to think about, okay, what if the storage, like a traditional commodity SSD, they also support the byte interface, and how should we are going to build the entire ecosystem for the storage system. So this is actually the point I want to deliver in the interface part. Okay. So now come back to the specialization part, and now come back to the program I just described. Because the storage system stack is so complicated today, and for example, the storage software lacks critical performance, and we can we build so many specialized storage system to address each of the problem. So for example, to make sure the performance becoming predictable in storage stack, and we can use the software-defined storage. We actually open the low-level hardware details to the application, and let the application to manage the flash chips. So in this case, we know when the GC will happen and when the address translation will happen. And this is one way how we can achieve the critical performance. And this is very critical for cloud infrastructure today. And to reduce the storage software overhead, as I just discussed, we can bypass the OS, and we can also use the flash as memory. And then, so we call the memory semantic SSD storage. And this is another way how we can, reduce, elevate the storage software overhead, because the file system overhead is high, and we try to bypass the file system, and we try to use the virtual memory and to access the storage devices. So this is another way, another type of specialized storage devices, storage system. And also, the storage software is energy intensive, and also the PCIe bandwidth is limited, and we can also build a specialized computation storage devices, to elevate the bandwidth bottleneck, right? So for example, we have the deep store and S-clave. We try to offload some, application functions into the storage devices, and also build the in-storage accelerator there, and to leverage the internal high bandwidth of the flash chips. So this is another type of a specialized storage system. And also to defend against the ransomware, and we can also develop many ransomware or SSD devices to defend against the ransomware. For example, we can let the SSD to detect the malware attacks, and we can also recover the data after the ransomware attack. But we can keep the list going on. But one question we have to ask ourselves is that what's the purpose? It's just for performance, or eventually we actually wanted to achieve higher goals. Is that we want to aim higher, right? So my takeaway for this part is that the specialization can be generalized, but it will take time, right? It's not just take a few years you can generalize something, but it will take a long time to generalize this specialized storage system. And actually, if you look at the history of the development of storage system, and you will realize actually, and our storage system is actually driven by the specialized systems, right? So eventually, the specialization can be generalized and drive the evolution of a storage system. And I want to use one example to show you that and how this can happen. Okay, so I'm going to use the ransomware aware storage as an example to show you that why this is possible. So I think when we talk about ransomware, and I think many of you may heard that in 2017 the WannaCry ransomware attacks happened, and it quickly compromised the more than 230,000 computers around the world, and it actually spread across more than 150 countries. And for each ransomware attack, and when they success, and they are going to ask the victims for $300 to $600. The reason why I use the ransomware as an example, because it's so close to our daily life, and it's really it's happening every day, and this is going to affect the way how we use the storage device today. So, and if you Google the ransomware now, and you are going to find many news about the ransomware attack, and right. So, for example, in the US, and the ransomware attack the gas pipeline, and in the eastern part of the US, and actually the gas pipeline stopped working for a few weeks, right? And also they ask quite a few $1 million to recover to get the data back for the system. So I don't want to emphasize more. I don't need to emphasize more how important the ransomware attack to defend against the ransomware attack today. So what's encryption ransomware? And it's actually very simple attack pattern, and they are going to try to identify the vulnerabilities in your system, and they encrypt your file, and they try to destroy the original file, and then after that they are going to ask for payment to decrypt the files. So this is the patterns of the encryption ransomware, and why the existing solutions are not good enough. So for example, we can rely on the malware detections to detect ransomware. The problem is that even though we can detect the malware, but the damage has already happened, right? It's already encrypted your data. If you want to get your data back, you still need to pay the ransom. And also we can rely on the journaling or log structure file system to maintain the copies of our data. But the problem is that the ransomware, they can't have the OS kernel privilege and they can still destroy the copies of your data. And we can also rely on the networking or cloud storage to the backup. And they have the similar issue, and the ransomware is they can actually compromise your system and terminate the connections with the remote cloud storage. And also, when we use the cloud storage, this is going to increase the storage costs and of running the IT system. So this actually drive us to think about what's the new threat model and when we defend against the ransomware. So we actually build a very strong threat model is that we do not trust any system software. So we do not trust application and user space malware detection or kernel space malware detection. We don't even trust the block driver. And we only trust the SSD firmware. And because the interface between the host and the SSD is so simple, and this actually can help us reduce the attack surface, right? Because we only have the read-write, the comments and between the host and the SSD. And so the goal and for our design is that we want to defend against the encryption ransomware and without rely on the software-based solution and without explicit data backups. So let me introduce why this is possible. And we actually leverage a very important properties of the flash-based SSD. And you may know that flash-based SSD, they only support out-of-place updates. And what does this mean? It means that when we overwrite our data and in the flash block, and we are not going to erase the block, and we are going to actually write the data to a new place. So the old data is still there. So in this case, we just need to change the garbage collection algorithm of the SSD, and then we can recover the data. And this is fundamentally different from the traditional hard disk drive. So when we overwrite our data block, we are going to physically erase the block in the HDD. So in this case, we actually can maintain the invalid data caused by the encryption ransomware. And in this case, we just change the garbage collection algorithm, and then we can recover the data after the ransomware attacks. And then, so we can maintain the data, the victim data, caused by the ransomware attack, and we can also make this approach even more generic. So if we can maintain the past storage state in a time order, we call it time traveling SSD, and we can actually maintain multiple versions of your data and in the SSD. And this actually is similar to the GitHub, right? You can maintain multiple copies of your data applications there, updates there. And we can also enable the system debugging, right? For example, if your system crashes, and we actually can rely on the time traveling SSD to recover the system. And of course, we can also enable the trusted storage forensics and investigations, right? If the bad things happen against your SSD and the policeman or FBI is going to investigate your devices, they actually can rely on the time traveling SSD to investigate, to build the trusted evidence chain for the attacks, right? So why the trusted storage forensics is so important? And this is actually based on our study of many ransomware attacks, right? For many victims after the ransomware attack, we realized actually many IT systems, they don't enable the post-attack analysis. This actually take a long time for them to recover the system. Right? For example, many IT systems, and only 20%, 24% of them, and they have the post-attack, and they can enable the post-attack analysis, and the analysis will take more than 6 weeks, right? And also, we cannot rely on the software-based approach to store the logs, right? As we just discussed, the malware, they may destroy the evidence, and they may manipulate the evidence. So build a trusted post-attack analysis. This is highly desirable, and this is actually how the architecture people can help here. And we actually rely on the flash-based SSD hardware to help them solve this problem. So because the storage capacity is very limited, and we wanted to maintain the other copies of the data in the SSD, and so we have to the solution is that we have to enable the data compression, right? So with the data compression, we actually can significantly reduce the storage cost when we retain the past storage state. And also we can further extend the retention time and for the for the ransomware around SSD, and we actually can adjust the retention time based on the write intensity of your applications, right? So for write-intensive workload, we can maintain the data for a longer time, and for the less write-intensive workload, read-intensive workload, we can maintain the victim data for longer time. And also, we changed as we discussed, we changed the garbage collection algorithm to maintain the data in time order. And the way how we maintain the data in time order is actually we are not going to track all the copies of your data and one by one use the direct page mapping. We actually use the Bloom filter, and we actually partition the time order in multiple epochs, and each epoch represents one time window. And then every time when we our page becoming invalidated, we just put the PPA and into the Bloom filter, and then so on and so forth. Right? When we pass the time, and we just remove this Bloom filter, and this is the way how we actually enable the time order Traveling SSD. Okay, so we actually use the real programmer SSD to build a proof of concept prototype to demonstrate that we can actually leverage the existing SSD to defend against the ransomware. And we have many ransomware samples to test our system. And we also use the commercial or standard storage workload to test the performance of the new SSD. So give you one example is that for different applications, we guarantee we are going to maintain the data for 3 days. This is actually good enough to defend against the many ransomware attacks today, right? Because many ransomware today, they are going to finish the attack as soon as possible and less than 1 hour. And if we can maintain the data for 3 days, it's actually offer great opportunities for the owners to recover the data. And with the adaptive window, we actually can further extend the retention time to more than 50 days, right? And also, we actually even can extend the storage capacity, local storage capacity with the networking storage co-design. So, for example, in traditional way, and when we do the data backup, we have to load the data from SSD and to the host, and then transfer through the networking card. And we propose a new design we call the networking storage co-design. Is that we integrate the networking card into the SSD controller. So in this case, actually the SSD can directly transfer the data out and from the SSD itself and fully bypass the host CPU. So this is the system architecture of the networking storage co-design architecture. And you can see we are on the left side of the figure, and we have the transfer buffer. And actually because the SSD controller has an embedded processor, and this processor actually can directly talk with the integrated networking card, and for us to transfer the retained data copies in the local SSD. So with this design, and we can transparently expand the local storage capacity, and that's the way how we can guarantee the local storage performance, and we can further retain the data, the auto copies of the data in the hardware for a longer time. And this also enables the hardware isolated data transfer, and because we can transfer the auto copies of the data and to remote trusted remote storage servers, and we can enable the ransomware detection and the post-attack analysis. So with this new design, and we can further extend the retention time. For example, the RSSD can retain the data for over more than 200 days. Okay, so now come back to the specialization, and I just use this example to show you that in commodity SSD, we don't have the storage property, but because the ransomware is so popular, and we are going to think about whether we can integrate the storage security properties into the device. And this is not easy. This is actually going to take a long time. So in 2017, and we actually started to look at this problem, and we published our first paper called FlashGuard, and to defend against the ransomware. And in 2018, and we received some attention from the government agency, and they are willing to work with us to further advance this research. And in 2019, and we built the Traveling SSD. And for the FlashGuard, we can only maintain the data for the ransomware attacks. And we are going to think about whether we can make this solution to becoming more generalized, right? So then we build a Traveling SSD, and we can not only maintain the data, victim data caused by the ransomware attack, we can also maintain the past storage state in the flash-based SSD, and we call it Traveling SSD. And in 2020, we actually, because of the contributions of the Traveling SSD, we actually received some attentions from the industry and then we received the IP license request and to further develop this technology. And then we also built a trusted execution environment for in-storage computing. And then in 2012, and we work on the networking storage co-design to further expand the local storage capacity. And we published a paper and ASP+ 2022. And then this work also received attention from the government agency, and we received new funding to continue work on this. And then this year we started to build our based on the ransomware around SSD, we started to build a hardware isolated time traveling machine. And this is not only for SSD itself, but also for networking devices and also GPU devices. We wanted to get this sub-component in the computer system, directly connected together and fully bypass the host CPU. So now you can see, right? So, yeah, go ahead.
Yeah, I'm sorry. I have one question regarding, the technique you explained for ransomware. So basically, you need to disable garbage collection for a few days, just to make sure that we don't erase the previous copies, right?
So we do not disable the garbage collection. We just change the garbage collection algorithm and to make sure they are going to clean the data in time order. So in traditional way, when you do the garbage collection, they just random pick up the victim blocks and erase them, right? And now because we are going to retain the data in time order, so we have to make sure the garbage collection and they are going to clean the data in time order as well.
I see. Yeah, okay, yeah. In traditional technique, it's not completely random, but I guess we don't
because we have to consider the time frame.
Yeah, we don't consider the time. But at some point, so you mentioned that we can run out of space capacity in SSD, and we need to copy data to a remote server. Am I right?
Yes. So that's the networking storage co-design solution. And you can keep the data local, but because the local storage is limited, and you can use the data compression to compress the data, and that's one way. But we realize it's not enough, and especially for future attacks, and that's the reason why we extend it to the networking devices.
Yeah. So how? I don't know. So how often we need to copy data to remote? Because to me, the data movement overhead for that can be actually high. Of course, you're addressing a very important problem, and we can also pay for that. But I'd like to have some idea regarding the energy overhead of those copies.
It's not a high frequency. It's actually you can offload. You can copy the data from the local SSD to the remote servers, and based on their estimation on the idle cycles of your local SSD, right? So for example, if you don't have much IO traffic in your local SSD, you actually can detect that, and then you just copy the garbage data, to the remote server. Because anyway, you have free blocks locally, and this actually can give you some time and to offload the data in the background.
Okay. Yeah. Thank you.
Yeah. Okay. Any more questions?
Professor, I have a question. So you mentioned about the post-attack analysis, remote post-attack analysis to identify whether there was a ransomware attack, right?
Yeah.
So I just wanted to know, because in an SSD we usually randomize the data and also do ECC encoding. So if the data is moved to the remote server, so is it how does the post-attack analysis work on the randomized data? That is one question. And also, what kind of primitives or what kind of signs are we looking at for detecting the ransomware, and can those be implemented for ransomware detection within the SSD itself?
Yeah, so for the first question, and we actually keep all the valid data locally. So we only copy the invalid data to the remote servers. And when we do the post-attack analysis, and it's not only about the data, it's also about your storage operations, right? So you wanted to figure out what happened in your SSD, for example, read write and erase operations. And we are going to maintain all these operations in your local SSD, and then we are going to compact them and then transfer them to the remote server for the future post-attack analysis, right? This is actually exactly how the FBI or policemen, and when they investigate a ransomware attack, right? They want to know what happened against your storage devices, and they wanted to build a trusted evidence chain to show that why the ransomware happened in the system, right? So this is actually the answer to your first question. The second question is that we can do the in-storage ransomware detection because you have the data, you have the trace, and you also have the processor, right? You actually can develop a very lightweight malware detection algorithm and to detect the patterns. And the problem is that the challenge part is that you don't have much semantic information of the system. You only have the block IO, the IO traffic there, and based on the traffic, you have to figure out whether malware is happening on your system or not.
Okay.
Yeah. Okay.
Thanks.
So I'm supposed to finish the talk in 1 hour, but it seems that I cannot. So I just do like we finished the discussion on the interface and specialization, but there's another things I want to discuss is about the approaches, right? So I'll come back to the programs we just discussed. We can build many specialized storage system, and we have to think about should we keep the list going on, and then every time we encounter a problem, and we just build a specialized storage system to address it, or should we think about a better way to develop the storage system? So that's actually the third research questions I try to answer over the past few years, is that what's the right approach to developing the storage system today. And I'm going to also going to use one example, the software-defined storage, to show that actually why we can use borrow today's machine learning approach to help us developing storage system today. And so what's software-defined storage? In traditional way, we use the flash-based SSD as a black box, and we run many applications there. And because it's the black box, and we don't know what's going on there in the hardware, and this is actually going to cost the performance, pretty good performance. Then the industry has ideas that, okay, let's open the black box and let's expose the hardware details, the flash chips to the application, so we can map each application to dedicated flash channels. And in this case, we can enable the hardware isolation and for different applications. This is a very simple way and for us to achieve the performance isolation and between applications. And this is also a way how we achieve the critical performance, because what's going on there. When the read-write are going to happen, and when the GC garbage collection in the SSD is going to happen. So, and with the software-defined storage, we can actually get many benefits, and this is also feasible. And with the software-defined storage, we can achieve critical performance, and we can also improve the storage utilization, because you can allocate the storage capacity based on the needs of the applications. And also for today's industry manufacturer technology, with the mature manufacturer technology, it's actually very easy for us to customize the storage devices today. And as far as I know, many industry companies actually build their own flash-based SSDs, right? And you can see that the manufacturer technology are actually well mature today, and it help us, enable us to customize the devices. So, but there's still a gap between the application and the customized SSD, right? So we wanted to leverage the mature manufacturer technologies to customize the storage devices for different applications, so we can achieve very good performance and also best utilize the hardware resources. But there are still many challenges. For example, and when we look at the SSD, we have a very large set of device parameters to tune it. And when you customize the storage devices, we have to decide which parameter we should tune in and which parameter we should adjust, right? And also, it's very hard to manually identify the optimized devices parameter for different applications, right? For example, for database application, KVL store application, they have different requirements on the storage performance, and they may require different hardware parameters to deliver and this high performance. And it's very hard for human being to just run many experiments to figure out what's the best parameter. And for the customized storage devices. So the traditional testing method has a very long tuning time, right? you may wonder, maybe we can build our testing framework to just test the different configurations and run different benchmarks, but this will take a long time. So we realized actually we can use the machine learning approaches to drive the software-defined storage. So for example, we study many different IO traces from different applications. For example, on the database and advertisement, key-value store, and the graph, and even search engine. And when we use the k-means and to cluster these IO traces, we find that actually for our the IO traces belong to the similar category of the applications, we actually can easily group them together. And this actually provides strong evidence to show that and we can use the machine learning approach to identify the patterns of the application, and then we map these patterns to the hardware configuration so we can customize. This will make us easier to customize the storage devices. So we believe the learning-based approach to developing software-defined storage is promising. So we actually built a framework to help us identify the best SSD hardware configurations for different applications. So giving our new workloads, and we are going to first use the k-mean cluster to identify the unique IO patterns of this application, and then we check our configuration database, and we use the similarity and the search to identify whether this pattern match with the existing configure, the workload patterns. If it's identified, then we just recommend these configurations to the developers. And if it's not, we are going to retrain the model and then tuning the parameters and then do the search space and then identify the best match, identify our new optimized configuration and for the new workload, right? So we are going to use the parameter pruning and to improve our tuning performance. And then after that, we are going to do the performance regression to identify and which parameters are sensitive to this workload. And we initialize these parameters, and then we use the heuristic tuning to keep and use the simulator to validate each configuration we learn with the model, and so on and so forth until we converge to our optimized configuration. And so this is actually the framework, a learning-based framework we built to help the industry, or even help the researchers in academia to identify the best hardware SSD configurations for the SSD. Okay, so here are some results we get from our study. So for example, we identify many SSD hardware parameters from the industry, and actually also some of them reference to the MQ sim built from honors group. And we actually when we use a very simple approach to do the pruning, and we identify that actually 45% of the parameters can be removed with the parameter pruning, and this is because these parameters are not very sensitive to application performance. No matter how we tuning these parameters, they are not going to affect the end-to-end performance. And then we identify, in the framework we set our target workload, right? We have different workload, applications, and for each category, and we set them as a target. And then we also have long target workload. And then the conclusion is that with the target workload, and we are going to rely on the framework to try to identify the best hardware configurations that can deliver the best performance for the target workload. And also we wanted to guarantee that the new configuration will not compromise the long target workload. So we get some good results from this study, and we can see that for most of the target workload, we can achieve 1.37 times better performance than the commodity SSD, and also without compromise the performance of the long target workload. So we use this example to show you that we can use a machine learning approach to help us develop specialized storage devices like the software-defined storage, right? So this is one example. And another example is that we can use the machine learning approach to best utilize the precious DRAM resources in the SSD kernel. We can actually use the machine learning to learn the address translation, and then so we can reduce the so we can utilize the DRAM efficiency there. So the motivation of doing so is that over the past decade, we have seen the commodity SSD have been well developed, right? So for example, the PCI interface has been well developed. We have PCIe Gen 5 and Gen 6 and have higher bandwidth. And then we can have more powerful embedded processors integrated into the SSD kernel. And also we can deploy more flash channels to increase the internal bandwidth of the SSD. But the problem is that the DRAM capacity is still an issue with SD kernel. This is because the the DRAM is very expensive, and also they have very limited capacity. So the SD DRAM is still the bottleneck. So now come back to the address translation in the SSD, and the traditional way when we index the flash pages is that we use the direct mapping, and we have the logic address and the physical address and one-to-one mapping. And for 1 terabyte SSD, if we use the direct mapping, and the mapping table is going to take a large space, about 20 gigabytes of DRAM to just cache the mapping table for 1 terabyte SSD. And if the page size is 4 KB, right? So the SSD capacity is further increased, but the DRAM and also if we increase the SD capacity, the mapping table memory footprint will also be increased. But the DRAM capacity cannot scale. So the SD DRAM capacity is less scalable. So we wanted to propose some solutions that we can, if we can reduce the memory footprint of the mapping table, and we can reduce the manufacture cost because we can reduce the demand on the SSD DRAM capacity. And this is also going to improve the performance for the storage devices because we can best utilize the SSD DRAM to cache the data. So that's the way how we can improve the performance. So here's the way how we use the machine learning approach to help us reduce the memory footprint of the mapping table. So instead of maintaining the mapping table one by one, and from the logic page address to the physical page address, we can actually use a very simple linear regression to learn the patterns of the address translation. So we can actually compact multiple entries of the mapping table together, and we just keep the starting logical page address, and then we maintain the length of the buffer, and then we just keep track of the slope of a set of the mapping table entries, and then we can use the learner index segment to represent this set of mapping address mapping entries. So in this case, we actually can reduce the mapping table size from the 32 megabytes to 80 bytes. So this is just one example to show you that how we can use the linear regression to compact the mapping table size. So with the reduced mapping table size, and we can reduce the memory footprint by 20.9 times, and with the reduce the memory footprint, and we can further improve the end-to-end storage performance by 1.4 times. But of course, build this learning-based flash translation layer or address translation is not easy. We have to overcome some challenges. The first challenge is that we have to avoid the learning overhead of the mapping table, because we are going to learning the address translations in the flash translation layer, and we actually maintain this learning the segment in the log structure. So this is the one way how we elevate the learning overhead, because we have limited CPU cycles in the SSD kernel, and also because we use the learning approach to predict the address translation, so the misprediction may happen. So we leverage the out-of-band metadata in each flash page. So in the out-of-band metadata, and we are going to store the correct address translation, the correct physical page address there. So every time when we do the translation, we are going to load the page to the SSD RAM, and we are going to use the OOB metadata to verify whether this translation is correct or not. And if it's not correct, we just use the stored PPA to figure out the correct PPA address of the corresponding logic page address. And also, this design is not going to affect the core traditional conventional FTL functions, and we still maintain the garbage collection and also the flash block allocation. We actually try to improve the flash block allocation to to further benefit the learning-based approach when we learn the address translation in the flash translation layer. So this is just another example to show that why we can use the learning approach to help us further develop the storage system. And we actually wanted to build a learning-based storage ecosystem, and from the device level and to the application level. So for example, we just discussed the learning-based SSD. We discussed how we use learning approach to customize the storage devices for specific applications. We also discussed how we use the learning approach to reduce the memory footprint of the mapping table in the SSD kernel. And we also try to build our learning-based file system so we can identify the hot data and versus the cold data, so we can do the better data placement. We also apply this learning approach to the cloud storage infrastructure. We can enable the learning-based storage harvesting to harvest the storage resources for different virtual machines in the cloud. And I don't have time to discuss this work, and please refer to the paper for details. So we actually have our kind of ambitious goal is that we wanted to apply the learning-based technicals across the entire storage stack. And this is just because the storage system today is becoming so complicated. It's very hard for us to just rely on the human-driven approach or heuristic-based approach. And we actually can leverage the advancement of machine learning technicals today to help us drive the storage system development. So to summarize my talk, and so in today's talk, I discuss 3 aspects of building storage system: the interface, and the specialization and approaches. I summarized them as the SA of storage system. And thanks for give me this opportunity to introduce our research. And most of the work, is not only done by me; it's actually done by our group, right? So it started the system platform research group and the USA in early 2018, and so we have already done a lot of works in the space of memory and the storage system, and we also try to build AI infrastructures today. And I encourage you to access our group website to learn more about our ongoing research project. And thank you. I think that's my talk.
Okay, thank you, Jian, for this very nice talk. I think I'll ask a couple of questions and then I'll let other people ask some questions also. If you could go back to the software-defined storage, that matrix that you showed, test and target applications. I had a couple of, here, I had a couple of questions here. So here, you're not doing this configuration changes dynamically, right? It's statically.
It's statically, yes.
Okay. Do you have any idea of what would be the potential if you actually do some dynamic changes? Of course, on those parameters that can be dynamically configured.
That's a very good question. Reinforcement learning. That's actually, for example, in the SSD kernel, we have the ARM processor there. And when the users deploy the SSD, and actually different users, they have different access patterns. If you can use the reinforcement learning to learn their patterns, you actually can decide the data placement and runtime, and that's one way how you can deliver good performance. I remember already our paper discussed reinforcement learning memory kernel. Actually, the similar idea can be applied to the SSD kernel.
I agree. Actually, we have another paper on reinforcement learning for hybrid SSDs, but that's a different thing. The Sybil, I think there's a lot of potential here. I was curious if you looked at it in this work.
So we are looking at this, and we are also very interested in collaboration.
Okay, that's great. Yeah, we should probably discuss further now that you've given a talk, and we can have a separate meeting for sure. That'd be great, actually. I had another question over here that now escapes me. maybe we'll come back to that question. I think I remember now.
Okay.
So this is this is also looking for a target metric, which is performance. Have you considered energy? Because by dynamically customize, even statically customizing or dynamically customizing, you can also save significant energy, right? Some parameters may be over provisioned, for example.
Yes, we actually consider energy. We, for different subcomponents in the SSD kernel, and their energy consumption will be different. We just use the power model, and then integrate this power modeling into the learning framework, and when they adjust the parameters, they are going to also rely on the SD simulator. They are going to figure out what's the total energy consumption and for different configuration. And this is actually another bounding box boundary, and when we do the design space search. Yeah.
Okay,
so
that sounds good.
Yeah.
Do you have any results on that?
We have some results, but I do not put it on the slides. But
Okay.
I can send them to you.
Okay. I mean, if it's in the paper, I can look, but I didn't get a chance to look at the paper.
Sure.
Yeah. Okay, I think I have one more question related to this direction. If you go to the slide where you give the overall picture of potential learning techniques, I think toward the end.
Yeah.
Okay, yeah, this one. Okay, yeah, I mean, I definitely like this, let's say, research agenda, and certainly think that there's a lot of complexity in the storage system, and we have too many heuristics, right? I think learning can help.
Yes, we call it self-driving storage or something like that.
Yeah, exactly. Now, of course, once you start putting learning in all of these different pieces of the storage system, the question also becomes, how do you coordinate between them, right? Maybe they're going to make decisions that are not aware of each other. Do you have any thoughts on that?
Yes, I have a very concrete example to show you that why we should do cross layer. So, for example, there's the database community is actually work on the learned index for a while, but they mostly focus on the software space. So, for example, and when you access the data in SSD, you can learn the index, and the learn index will help you save the memory and also help you improve the lookup, right? So the metadata lookup. But the problem is that if you do not consider the hardware event, and the hardware is actually going to mess up your learning, the learning index, right? And for example, you have a logical page address on the host side. You have the physical page address in the SSD. And you also have a learning flash translation layer there. And if you do not enable the learning there, and the flash translation layer actually going to mess up your translation, your learning index. And this actually will make the upper level learning index inefficient. So that's actually one concrete example of why we should do cross layer. And then because, as you said, the stack is so complicated, we have to be take some effort to figure out how we do the cross layer and across the entire stack.
Mm-hmm. Yeah, I mean, certainly it makes sense. If you do cross layer, you can coordinate better. Yeah.
Yes.
I think one last question related to this. Clearly, learning techniques that are employed for these different problems also need to be different, right?
Yes.
Yeah.
For example, based on my interaction with the industry, for example, when we work on the learning-based storage harvesting, and they very worry about the learning, the CPU cycles consumed by the learning process, right? Because they are going to deploy the system in reality, and they don't want to deploy a GPU there just for enable the learning-based storage there. So actually, for different layer, and we can try different learning algorithm. And the principle is that we have to make sure the learning process is as simple as possible, and also try to minimize the consumptions on the CPU cycles. Yeah.
Okay, makes sense. I think that's all I have for now. But
and also, for the hardware devices, when we work on the self-driving SSD, and actually because the processor there is less powerful, and you actually don't have opportunity to develop a very complicated model like a deep learning model, right? You have to just use some very simple model to learn the data access patterns.
Yeah, exactly. Or otherwise somehow offload the learning somewhere else.
Yes.
Yeah. But in any case, learning doesn't come for free, right? There'll be energy consumption also if it's expensive learning. Yeah.
Yes. So for the entire storage stack, we have a rich data set. We have it's very easy for us to get many IO traces, and we can track many events there. And so we have the data, we have the input for the learning, and we also have some processes there. Now, it just depends on what kind of machine learning algorithm we want to deploy there. and what's the target of the learning. So.
Sure. Okay, thanks. I think Mohammed may have a question. So I see him. But...
Yeah, thank you. Thanks a lot, Jian, for your excellent talk.
Thank you.
Yeah. I just forgot my question.
Okay, so we can discuss offline.
Mohammed, if I can ask a question.
No, actually, I remember now.
Okay, well, please go ahead.
Yeah, sorry. So, so for learning-based FTL design that you, explained, maybe I actually missed that part. But have you also considered page allocation in the FTL implementation?
Yes, we actually it's not a page allocation, it's actually block allocation, right?
Yeah,
in the SSD. So when we actually allocate our buffer, and every time when you receive the writes, you are actually going to catch the page in the buffer. And the buffer actually offers the opportunity for us to learn a good pattern, right? We are going to sort the pages based on their logical page address, because we use the linear regression, right? We wanted to just let me give you just come to there. So you can see that we have the slope, right? And the best case is that if everything is sequential, it's very easy for us to learn a very good pattern, right? So we just use a very simple segment. We can represent a bunch of address translation entries there, right? The mapping entries there, and so that's the maximum, memory saving we can get from there, right? So we actually use the block buffer to help us, introduce more opportunities for us to learn a good pattern.
I see. Yeah. Because so one problem that we observe in SSD is basically read conflict that we have, and when different read IO read accesses, they target different flash chips, but those flash chips, they are sharing the same channel, and we have basically conflict in the transfer. So I was wondering if you also consider solving this, at least mitigating or reducing this overhead of conflict with your basically learning-based FTL design.
This is also actually, this is a good point. This is actually also related to the learning overhead, right? So for example, if you keep updating the same flash page, you have many other copies, your address actually will also be updated, right? You have to be learning the segment, right? So to solve this problem, we actually build a log structure. We actually organize the learning segment in like a log structure merge tree. So we are going to, every time when you're learning a new segment, you just put a append to the log structure. And so every time when you do a lookup, you are going to go from the higher level first, and you are going to search the recent learned segment first, and then layer by layer, and then so until you find the correct address. So that's the way how we actually avoid the conflict, and also make sure every time you can get the correct address. And then we are going to do the garbage collection later. So because if you keep attending learning the segments into the log structure, the log will becoming very long. So we actually have set our boundary there, and we just needed to do the compact them after they reach the threshold.
Okay, sounds excellent. Thank you.
I have a question. So thank you for the nice talk. So on the learning segments, learned segments, I just wanted to know how it reacts to completely random workloads where you don't have a pattern for accesses. So does it work similar to the current FTL mechanism where it maintains logical to physical mapping?
Yeah, that's also a good point. So for the random workload, we just switch back to the regular page level mapping. So we cannot do better than the page level mapping. That's the worst of it. Yeah.
Okay. And another broader question is also that in recent years there is this move towards moving the FTL functionality to the host with open channel SSDs. So with more computation power, we can utilize machine learning techniques there to improve the SSD performance. But I just wanted to get your opinion on that direction and whether it's something that is pursued by the industry, and what do you think about that?
I think that's part of the software-defined storage, right? That's part of the software-defined storage. I think that's still a very interesting and a good direction to look at. I think especially for bigger company, I'm sure they are working on their own software-defined storage attack. And then when they deploy the FTL in the host, and that's exactly the topic I just discussed with Honor, why we should use the cross layer to learn the index, right? So you move the flash translation layer into the host, and then you can rely on the host to learn the index. But if you don't consider the underlying hardware events, and your learning will becoming less efficient. So then we have to do the cross layer to do the learning. Yeah.
Okay. Thank you.
Thank you. Any more questions?
Yeah, not from my side.
Okay.
I'm not seeing any question on YouTube also. Any more question from the Zoom audience?
Okay, it sounds like there are no more questions, so we're done. Thanks, Jian, for this nice talk and answering the questions. Yeah, certainly very interesting work.
Yeah.
Yeah.
Hey.
Sure, and we'll be in touch. Take care.
Yeah. Yes. Well, see you and Iska. Okay.
Bye-bye.
Bye.
Thanks a lot. Bye.